All right, on to lecture 10. So, lecture 10 takes us one step further in what we have been discussing this entire semester. It encapsulates everything that was all the way back from chapters 1 and 2, all the way up into chapter 8. Actually, I think chapter 7, I think. Maybe chapter 8. Anyway. So we're going to run through this. It's going to actually go pretty quick. There's a lot of slides and a lot of information, but this is really the test of how much of that information you gathered last time when we went through it. So what we're doing is that we are taking everything that we knew that was linear, and we are now putting it into angular. Okay, so instead of things going in straight lines, they're now going to go in circles. All right, so we'll go ahead. Let's just jump right in. The first thing that we learned way back when, I think it was lecture 2 for the most part, maybe even lecture 1, was things like position, terms like position, velocity, acceleration. And you should have a very good handle on what those things are now. And we're not changing them very much, but these new angular variables, they're just going to be the rotational or the angular versions of the things that you already know, those linear variables that you already are acquainted with. So the first one is angular position. So when you had regular position, we called it x in the initial, in the first couple chapters, and then we talked about, well, x is the same thing as y, it's just in a different direction, and if you took a change in x, it was known as a displacement. All right, so the same thing goes here, except for now we're talking about an angular position. So I want to bring your attention down here towards the bottom onto this this metal disc or this wafer or CD or DVD, whatever we want to call it. It's a round object that's going to rotate about the center, the origin. That's what the O stands for. And we're just going to pick a reference line. And I mean, it's pretty common to just grab a reference line on the x-axis, positive x-axis. As you can see, the disc being round and uniform, it doesn't matter where we actually pick it from, being it's the same everywhere. But we'll pick a reference line that's along the x-axis. Now, we pick a point on the disc, a point P, for instance, here. That point P was going to be defined by a radius away from the center. Okay, so we have a radius r, and there's a point P on this disc. Now, as we undergo a displacement, not linear, but a rotational, this disc rotates, and it will have a displacement of an angle theta. Okay, the radius here stays the same, but you see now point P has moved from down low to up top, and it has gone through a displacement of an angle theta. That is the angular displacement. So you see here the path that point P actually took from the initial here to where it ended up here on the final. It traveled a distance s. Okay, so they call that the arc length, the length of the arc that it traveled through because of that motion of theta. So there's a couple of equations that go with that. Hopefully you've seen these before, but s is normally denoted as the arc length, s, and it's just equal to a radius times theta. Okay, whatever the radius was that you stayed at and you rotated through theta degrees or theta radians, s will be the arc length that you get out of it. Okay, we can rearrange that equation, of course, to solve for theta, being this is all about angular variables, so we would want to solve for the angular variable theta. And that's just s over r, it's just rewriting the equation. Now, if we have theta and we change theta to a different theta, we have done a displacement of angle, right? So that's how we get the change in theta. Now you saw this is change of x is equal to x final minus x initial. Here, the angle has changed from a final angle minus the initial angle. Okay, so you can see that here in this plot we have the x and y axis. We started off with some theta here, some angle, and then we push that piece even further, and we have now a larger angle, theta f. Okay, so this would be the displacement. This is the change in theta. Displacement, so angular displacement or angular position change. Okay, both of these are angular positions. Now, of course, it'll take some time We have point B here at TF, and we have point A here at TI. So initial time, final time. And it underwent a displacement in that time. So we learned early that a displacement over time is a velocity. But here we have theta being our displacement, so it's an angular velocity. And we can't call it v because that's the same term, so we give it a new term, w, or omega. So omega is equal, just like we had before, where it's the displacement, change in theta, over the change in t. And this is what's known as the angular velocity. The same, of course, will follow suit for angular acceleration. Angular acceleration, we can't have it be a lowercase a, so we give it a new term. This is a alpha, Greek letter alpha. We also kind of call it fish sometimes because it looks like a fish. It has this tail effect on here, so it's not an a, it has this extra tail. And it is the angular acceleration. And of course, angular acceleration would be equal to the change in angular velocity over time. Okay, so this brings you three new things, three new properties. We have angular position, angular velocity, and angular acceleration. And those three things can lead to lots of changes and other things that we already are aware of, things that we already know. Okay, all right, hopefully that makes okay sense. We're now changing angles, that changes everything. Okay. What about the kinematics? We're so used to seeing these VF equal to VI plus A times T. How is this going to work, being that these all have linear properties? Well, they all work the exact same. They all work with angular variables as well. You can change the VF linear velocity, you can change it to angular velocity, but the rest of the equation also needs to be changed into its angular form. So instead of V's, you're going to use W's. Instead of A, you're going to use an alpha. Of course, T remains the same. Time doesn't change whether you are moving in a circle or a straight line, so T for time remains the same. And you can see I've made the changes on all four of the kinematic equations that we're already used to seeing. Okay, you just change them into angular. It's just important to make sure that all the variables are angular. You cannot mix and match the two without doing a proper conversion. They're not one-to-one. You can't just pull out alpha and put in A. That is not how they work. I'll show you the conversions later in the chapter. Okay, so as long as it all remains angular, you can make those substitutions. How to go from one to the other. So here's how we can swap one to the other. If you go from angular to linear, it is dependent on the radius, usually. All right, so let's see this trend, and it's going to continue for a lot of the other equations that you already know as well. You got the first one already. This is a length. You can think of this almost as an x or a y, a length. It's equal then to r theta. It's dependent on a radius. Right, so the linear term is equal to a radius times the angular term. Okay. It works for the others as well. If you want linear velocity, it's equal to a radius times the angular velocity. Okay, it's just a radius times the angular term, brings you back to the linear term. And of course the same for acceleration. Here they've done a subscript t. You'll sometimes see that in different books and other forms. It's just denoting that it is the linear term for acceleration, and it will be the radius times the angular acceleration. We can also work with centripetal acceleration. Centripetal acceleration, which we had already learned, had the lowercase c there in the subscript. We knew that was velocity over radius. That already had a radius in it. If we substitute v for rw, like we see up here for our substitutions, we will end up with centripetal acceleration equaling r omega squared. Okay, so it's a new term for our centripetal acceleration, and it also shows you the change in all of these other equations. Okay, all of our other forms of equalities here in order to change out and swap. And you can do that back on all the kinematics if you wish, but you'll notice that both sides are going to have an r times everything, and the r's then will cancel out of both sides. And that's why you end up with the kinematics the way that they are. Okay, but here this trend will actually continue on. Here's how you go from one to the other, which you'll have to do several times. Okay, going from linear, straight line, to angular, rotational. Okay. So we talked about position, velocity, acceleration. That was chapter 2. Then we talked about motion. That was chapters 3 and 4. Two-dimensional motion, kinematics. So that covers that. The next topic that we looked at was forces. And of course, yes, there is an angular force. It will follow that same trend of multiplying by r. The angular force here is known as torque. Torque is going to be written as this Greek letter tau. It looks like a capital T, but it's a little bit small. But you'll notice this, it has a hook on the one side. Actually has a little hook on the other side as well. But this Greek letter tau stands for the torque, and it is equal to a radius times force. Okay, so exactly what you would expect, with one caveat on here. Forces have vector components, and it's important to note that only forces applied at 90 degrees from the rotational axis matter to us, okay, on torque. So you can kind of see it here with this wrench. It does get a little bit confusing, but in order to get that 90 degrees to take effect, we have to add in an extra term, a sinusoidal wave or a sine wave. And it depends on an angle. That angle, which here they've used phi, the angle there is the angle between r and f, okay, between the radius and the force. The angle here always depends between these two, which we saw earlier with cosine, right, that it was the angle between these two objects. Same applies here, but we want it to be at 90 degrees now. And you can see kind of by the demonstration of the wrench, if you're trying to turn this nut, the r is the length of the wrench, okay, and the force you apply, the nut will only turn if you apply a force that is 90 degrees to the radius. Okay, this other force, this F cos phi that's being pulled off to the side here, this isn't going to turn the wheel at all. This is just pulling on the wrench. It isn't going to turn the nut. So this one doesn't apply to anything. Only the 90 degree one will actually result in a turn. That is why we have the sign of an angle in here. Now sometimes they call it FD. You have a force. They've determined this distance here. This one gets a little bit more complicated because you've got extra things going on. I like to just use the first part of this equation, RF sine theta or sine phi. Okay. So that's this force. Okay. Torque is known as the angular force. Well, now that we know a little bit more about torque, it explains a lot more about the moment of inertia. Now, we're going to apply that same logic for torque as, well, if torque is just equal to force times the distance, let's go ahead and calculate out what that is. We'll use our standard force equation to get a generic standard definition for inertia. So here they have the sum of all the torque, okay, sum of all the forces. Angular forces. Well, we know that the angular forces of torque are just radius times a force. So here they've omitted the sine theta because we're going to go ahead and assume it's 90 degrees for our derivation here. Force and a radius multiplied together. Well, what's the generic term for force? The generic term for force is ma, right? F is equal to ma. So we'd have ma times r, okay, for torque. Okay, so torque is the angular form of force. A is the linear term for acceleration, and then we have times r. So we need to get rid of this linear term for acceleration, put it all in angular. So how do we get rid of acceleration? Well, 2 slides ago I showed you how the conversion to get from linear to angular, right? So the linear term a turns into an r alpha. Okay, that's how we go from linear to angular. So this a turns into r alpha, so now we have mr alpha times r. Okay, and then we're just going to rearrange this equation just because something magical happens here. Take that r, bring it in, so you get an mr squared, and then times alpha. Now, torque is angular force. Alpha is angular acceleration. Well, what the heck is this mr squared? Mr squared is actually the angular type of mass. Okay, it's kind of weird to think about, but if you remember way back when, I did warn you about this one, that mass has a strange definition. My definition of mass is how difficult it is to move an object in a straight line. Difficulty to move an object in a straight line. Okay, that was what my definition of mass was. To make that angular, it would have to be the difficulty to rotate an object. So I have to give it a new term, and that term is the moment of inertia. I is equal to mr squared. Now we have angular force, torque, we have angular mass, I, and we have angular acceleration, alpha. Now we have angular everywhere showing up in this equation. So this is the angular version of the force equation. F is equal to ma. Okay. It's important to note, if you do have more than one mass, I, the moment of inertia, will be equal to the sum of all of those masses times all of their radiuses squared. Okay, so there might be a couple of work if you got a couple of pieces of moment of couple of different masses. You'll need to find what all of those masses are, and you have to find all those masses and their distance, their radius from the point of rotation. You don't need to do this much. There might be a couple of examples of it. I'll try and make them as simple as I can. Most of the moment of inertias will be given, and there's a bunch of different types, which we see here on the next slide. So the examples of moments of inertia. The first one, these are just the common ones, but every object does have a moment of inertia of some type being rotated around some axis. But let's look at some common ones that you'll see in homework problems and exams. The first one is the hoop, or you can think of it as a thin cylindrical shell. All the mass here is on the outside, the outer rim. There's nothing in the middle, it's hollow. So all of its mass is on the radius r. So if you added up all of the mass, multiplied it by r squared, you get exactly what you would think. I for a hoop or a cylinder is simply mr squared. All of the mass is at the same radius r, so when you add it all up, you get mr squared. Okay. Now, a hoop or a shell is different than a solid cylinder or a disc, right? So we have a hollow interior. Here we have a solid cylinder, or if you took a very small slice, you'd have a disc. That mass is now distributed all the way from the center all the way out. So all of its mass is not at the outer rim. Normally, to do this, you'd have to take an integral. Being that this class has a few common examples here, we won't get into that. But it would be a given that the solid cylinder or disc averages out. The mass inside here averages out, so you end up with exactly half. So the moment of inertia, when rotated around the center of mass, you get 1/2 mr squared. Okay? M would be the total mass, r is the radius, squared. Now this can get a little bit more tricky when we have a in-betweeny, right? You have a cylinder, but it's not exactly thin-walled, but it's not solid. It's halfway in between. Well, we have a moment of inertia for that. Okay. That's just 1/2 the total mass, and then it's the two radiuses, radius 1 squared plus radius 2 squared, okay, on where the mass begins and where the mass ends. This one's not too common, but it might come up every now and then. Rectangular plane kind of works the same way as the hollow cylinder, except for here we have 1/12. So whenever I'm dealing with these, I always like to look at it like a ruler, because you have the 12 inches. So it's 1/12. The total mass, and then you have a squared plus b squared. So similar to the r1 squared plus r2 squared, you'll have the width a squared plus the length b squared. Okay, moving on to rods. Here we have a thin rod. If we rotate it around the center of mass, we'll have the moment of inertia around the center of mass. That's the rod being rotated around its midpoint. again, you're going to have 1/12 showing up. Okay, 1/12 mass times the length squared. So this one just has the one dimension length squared, and that's the moment of inertia for a thin rod. You can see if you go off the center of mass, like in this example, where now you're going to rotate this rod along the end, it changes the moment of inertia drastically. You go from 1/12 ml squared to 1/3 ml squared just by changing the point of rotation. And the reason here is you have mass which is kind of equally proportioned on both sides. Here you have mass all on the one side. As the radius continues to grow, the mass is further and further out. So that does change the moment of inertia depending on where you're rotating it from. Okay. The last two examples are solid spheres. So this would be something that's very solid. You can think of like a pool ball, billiard ball in that case, not like a blow-up ball, but a pool like billiard ball. Something that is completely solid inside. Bowling ball, something like that. A solid sphere is 2/5 mr squared, and a hollow sphere, so like a tennis ball or a ping pong ball, is only 2/3 mr squared. Okay, so again, these ones are very common. They're going to be given in a lot of the problems. If you're in the algebra course, I'm not going to make you derive any of these. If you're in the calculus-based course, keep watching. We'll talk about how we find moments of inertia. Okay. So now that you've seen some of the examples for moments of inertia, you can kind of guess at what kind of problems we're going to be having now. These are going to contain angular rotation, so there might be something like a gear on the back wheel of a bicycle being turned by a chain. Well, the chain is what is causing the torque for the wheel to turn. It's applying the force, right? And the wheel spins around with an angular velocity. The tire sits at a specific radius. You can kind of see where maybe these questions are going. It's also why you have different gears on your bike. If you've shifted gears on your bike, you'll notice that the chain switches to different sized gears. That's increasing and decreasing the radius. That changes the torque. That allows you to go faster or go slower. Well, if you're not into bicycling, maybe you're into arts and crafts. So here we have a clay potter's wheel. The clay potter's wheel, if you've ever seen them making like vases or bowls or anything like that, it takes a bit of work. The clay actually has to be very well centered in the center of the wheel so that it spins correctly. And then you manipulate the mass. You start pulling mass to the sides. You start building mass upward in the y direction. You're constantly changing and influencing that object's moment of inertia. Okay, and we can ask all sorts of questions on that. We can ask for the speed of the potter's wheel. We could ask how many rotations does the wheel go through. Lots of interesting questions on wheels. If you're not into pottery, maybe you're a techie, data on a hard drive, on a hard disk, or a CD or DVD, or basically anything that's storing data that's on a disk. There's data on it. To read that data, it is essential that you know the speed at which the disk is spinning and where, the radius, where on the disk it is located. Okay, so we might have problems like that about gathering data off of different pieces of the disk. And finally, I'm sure everybody in here is probably related to a washing machine at some point, hopefully. Washing machine drum, right? If you have an empty load in the washer, the drum spins very freely, everything seems fine. I don't know why you'd be running an empty load other than maybe cleaning it. But as you throw in more and more clothes or heavy objects or shoes, you will notice that the washing machine drum starts to kind of oscillate around. It's because you're changing that moment of inertia, right? And if you change it too much, you're going to end up with a broken washing machine. Well, we might have some questions about that, about washing machine type kind of questions where there's a drum that's moving and something is added to it. Okay, so these are the type of questions you can look for in the coming homeworks and examples. Okay, so I said I was going to get to how to calculate moments of inertia. there are a few ways to calculate the moments of inertia. Again, for the algebra-based class, you don't need to worry about the limit. You only need to worry that the moment of inertia is simply the sum of all the masses times the radius squared. And that's it. Masses times radius squared. So there'll be maybe 4 or 5 masses. They'll all be at different radiuses. You're going to add them all up, and that'll be your moment of inertia. If you're in the calc-based course, okay, we now have to take a limit as mass approaches 0. So you're taking smaller and smaller pieces of mass, and you're going to add them all together. If you do that, if you sum up infinitely small pieces, you end up with that stretched S sum, which is an integral symbol. You're going to integrate. You're going to integrate all of the radiuses with respect to mass. Okay, so there's going to have to be a breakdown in mass and an integration done, integral. Okay, and if you're in the calc-based class, there'll be some examples on that too. Now, there are a couple of things that can help us with it. There's a theorem out there known as the parallel axis theorem. So the parallel axis theorem helps us calculate new moments of inertia based on old moments of inertia. Okay, so what do I mean by that? Well, think of a merry-go-round. Okay, I know that's an old concept to think of, but they still have things like a merry-go-round in parks. The merry-go-round, of course, is just a standard solid disc that spins around a center. That has a very easy center of mass moment of inertia. It's the disc moment of inertia. So 1/2 mr squared. You can easily calculate this one if you happen to know the mass of the disc. Now, let's say you take a person and you drop them onto the merry-go-round. You've now changed the moment of inertia, right? You've added a mass to it. So what you can do with the parallel axis theorem is that you look at the disk when it's empty, and you take that moment of inertia, and then you add every change that you make to it. So in this case, we're adding a mass at some distance d. So we're adding mr squared just from here. Okay, we're adding in an extra mr squared, and that'll give us a new moment of inertia. So it's a little bit hard to do here in the video. I'll do it on the whiteboard for you. I'll show some pictures and drawing that out and how the parallel axis theorem works. It's a nice, quick and easy little way rather than doing an integration or something like that. Okay, how about angular energy? Well, yes, there's angular energy. Just like everything else, we just need to put it in the same terms. Okay, so let's substitute all of our energy terms for angular terms. So normally we would have kinetic energy be 1/2 mr squared, or sorry, mv squared, 1/2 mv squared. That was our kinetic energy. Well, we now know that we can substitute mass with I and get 1/2 I, and then v gets substituted with a w, with omega, so that we have 1/2 I omega squared. Okay, so this is all the rotational terms for kinetic energy, and it gives us a rotational kinetic energy. So you see here we have a K with a subscript R. I will be doing the same. We'll have kinetic energy, but this will be rotational. So we'll have a KER for rotational kinetic energy. That means we've added a new type of energy to our list. We should now have 4. 2 forms of potential: gravitational potential, which is dependent on Y, and spring potential, which is dependent on there being a spring involved and a displacement in that spring. Okay, so those are 2 questions to ask. Is there a change in Y, or is there a spring involved? And now we have 2 forms of kinetic. We have the original kinetic energy, 1/2 mv squared, where you'd be asking yourself, is there a change in velocity? Now we also have a rotational kinetic energy. So another question you need to ask yourself is the object rotating in the problem? So you'll notice now we're going to go from square blocks sliding down a hill to a ball or a sphere or a disc rolling down a hill, because that will have rotational energy added to it as well for our energy problems. Okay, so I understand that was a lot of new information, a lot of new equations. Hopefully it wasn't too confusing or anything, being that it's just a substitution for linear terms to angular terms. But there actually wasn't a whole lot changed. Just this quick little review. We took mass, which is denoted with an m, and we converted it here into a moment of inertia. Now these, again, remember, are not straight conversions. Okay, you cannot just simply replace any type of an m that you see anywhere in an equation with an I and have it be correct. It has to be all or nothing. The entire equation needs to be either linear or angular in order to do that. Okay, but we've related what mass is to moment of inertia. We talked about position, how this originally was just an x or a y. We've now given it a new term, theta, whenever it's in an angular form. Same for velocity. V went to a w if it's angular. A went to an alpha if it's angular. And force is now a T for torque if it's angular. This actually should be a tau, but I couldn't find it in the symbols. But it should be a tau logo for torque. Okay, so I know that was a lot of information. Let's head on over to the whiteboard and let's do a bunch of examples to get you used to this and comfortable with using the new terms. All right, chapter 10 is going to be a big one here, so lots of new equations that should hopefully look just like old ones. So we'll start here with example 1. I have written down the new angular quantities up here, theta, omega, and alpha, which is the replacements to linear position, speed or velocity, and acceleration. It's the angular forms of that. And then I have also written up the kinematic equations with their new angular quantities present in them. Okay. And I've given you a question. For example, 1 is a 3-parter. We have a wheel that is spinning with a constant angular acceleration of 3.5. So anytime that we have something like this that is spinning, we're going to have now angular quantities to add into it. So this angular acceleration of 3.5 radians per second means that the wheel is speeding up. Okay? It's getting faster and faster. It has an acceleration. Just like a regular acceleration in a linear format, angular acceleration just means that it is speeding up rotationally. Okay? So it speeds up with 3.5 radians per second squared. Now that's the normal unit for that. We deal with radians when we deal with angular. Part A says if W, so that's the angular speed, if the angular speed is 2 radians per second at t equal to 0, what will the angular displacement be at t equal to 2 seconds? Okay. So when we have these, does it sound kind of familiar? We're given some numbers, we're given times, we're given speeds, we're given accelerations. It sounds like we have some kinematics. It should. So let's go ahead and write out our kinematics. Now, angular only occurs in one dimension, so, well, it's rotational. Okay, we don't have an x and a y, which means we're only going to have one set of numbers. Okay, we're going to have the change in theta. We're going to have the initial velocity, the final velocity, the acceleration, and time. It's just the new angular variables are going to be associated with them. So first off, what are we given and what are we looking for? It told us that the angular acceleration was 3.5 rads per second squared. Acceleration is given by the new term alpha. So I'm going to add 3.5 to our list. It also says if the speed was 2 radians per second at t equal to 0, that's the initial speed. T equal to 0 would be the initial. So our initial speed is 2 radians per second. What will the angular displacement be when t is equal to 2 seconds? So I am looking for displacement. And how much time has passed? 2 seconds. All right, I'm given 3 out of the 5 things. Hopefully now we see that this isn't so hard. I'm given 3 out of the 5 things. Which one do I not care about? I do not care about the final velocity, even if it's angular. I look up there and I say, which equation does not include final velocity? It's number 2 here in our case, which is given here by this one. And that's what I'll use to solve it. Okay, so I don't know what the change in theta is. That's the displacement. But I'm going to set that up equal to omega I, which is 2, times time, which is 2. So again, pulling from this equation up here. Okay, omega I t plus 1/2 alpha 3.5 t squared. Okay, so it's just like what we did with the kinematics all the way back in chapter 2, one-dimensional kinematics. Okay, so it shouldn't be too hard. We're going to have 2 times 2, which is just 4, plus we have this half times 3.5 times 2 squared, which is 4. And that'll give us, oops, screwed that up. 4 plus 1/2 times the 3.5 times squared. Gives us 11. Now you might be wondering on what are the units. I thought we were dealing with angles and stuff. So the units are in radians. Everything else is in radians. Those are all in radians per second. Radians are just like degrees. It's just a different form. Okay? So that gives us 11 radians. I'm going to put 11 radians up here. You might be asking, well, what is a radian? I didn't really go over that. Well, if you make one complete circle, what do we call that? We call that 1 revolution, right? What's revolution equal to? If we looked at it in degrees, for instance, 1 revolution would be 360 degrees. If we're talking about radians, that's equal to 2 pi. 2 pi radians. It's just another way of measuring angles. That's all that it is. All right, so halfway around the circle is 1 pi. All the way around the circle is 2 pi. So we can see here 2 times pi, roughly 3.14. So this is going to give us around 6 radians for a full revolution. So 11 radians means we went more than 1 revolution. We could do a conversion if you'd like and convert this into degrees. I'd rather you keep it in radians for your homework and exams, okay? Because it's the SI unit for all of this. It plays a part. If we want to convert it into degrees, we sure can. Okay, I know that every 2 pi radians is 360 degrees. So I could have, yeah, I'll do it down here. That's fine. 11 radians multiplied by 2 pi radians is equal to 360 degrees. And then you get a little better idea on how many degrees that is. Okay, so we do 11 times 360, and then we divide it by 2 times pi, and make sure you have parentheses around that if you're doing your calculator. And it's around 630 degrees. Okay, maybe that feels better to you, 630 degrees. Okay. Roughly the same. We did have to round a little bit on the degrees, but roughly the same. There are 11 radians or 630 degrees. Okay, hopefully that makes okay sense. That's the displacement. It started and it went through 11 radians, or it went through 630 degrees of rotation. Part A is done. This was part A. 11 radians. Part B. How many revolutions did the wheel go through during that time? Okay, well, we know it made it past 1. Did it make it past 2? We're on 11 radians, and I know that every 2 pi radians is 1 revolution, so we do another conversion. 11 radians. We're going to put 2 pi radians on the bottom because I want it to cancel, and that is 1 revolution. Here we are. We're doing unit conversion again all the way back to chapter 1. Radians cancel out. We're left with revolutions. Take 11 divided by 2 pi. you should get 1.75. Okay. How many revolutions? Well, on this one we can say that, let's just go over here. For part A, I'll go ahead and just put the displacement is 11 rad. For part B, 1.75 rev for revolution. And finally, part C says, what is the angular speed at 2 seconds? Okay, well, to determine the angular speed, we got to come back over to our table and get rid of some of this work here, but we're not done with our table, so we got to finish it out. Okay. The only thing left to do is figure out what the final speed is, which would be the angular speed, the final speed at the 2 second mark. Well, now that I have everything, I can get rid of this A up here if I want. Now that I have everything, I can go ahead and pick any of the equations that have final velocity in it. Right? So why not grab the first equation? That's what we usually use for this anyway. So that has the final velocity in the beginning, and then the initial velocity, which was 2. So we're grabbing equation 1 plus 3.5 times 2 seconds. Okay, so it's the same thing as VF is equal to VI plus AT, except now we're using angular terms. Omega F is equal to omega I plus alpha T. Okay, so what does this equal then? We grab our calculators, we do it again. We do 2. Well, it's 2 plus 7. That gives us 9. Okay, our final speed is 9 radians per second. We can add units to all these if we want. You don't have to. You certainly can. Okay, gets you used to writing down units. That's fine. So it's sped up. Well, you would assume it's sped up. It has a positive acceleration. It is speeding up as time goes on. So our final t at 2 seconds is omega f is equal to 9 rads per second. And that would be our final answer there for C. So you see how these are very similar to the kinematic equations that we used in chapter 2. Very easy. It's just a switch of variables. Once that clicks, it should make good sense that you can use these for those kinematics, and to be looking out for those kinematic quantities or qualities that in a problem that kind of shout and go, hey, kinematics will work here, right? It has to give you 3 out of the 4 items in order to solve for it. Build a table, do it out. All right, hopefully that works out for the kinematics. I'll move on to the next part because we have a lot to cover here in this chapter. Okay, welcome to example 2. This time we're going to deal with torque, being you've already had a lot of experience with kinematics. I think you'll be all right with angular kinematics. There's plenty on the homeworks to do and lots of practices out there. So we'll move on to torque. Torque can be written a couple of different ways. I've got the equations up at the top now, including torque. Torque is written with this tau, this Greek letter tau, which is kind of like a T with a funny top. Tau can be written as I alpha, or moment of inertia times alpha. It can also be written as force times a distance, like force times the lever distance, or a delta R, sine theta, or it can be as a cross product if it is in vector form. So I've got 3 different examples up, all of something pretty simple. So I'm going to say that this is a door, like a top view of a door. And here you've got the hinge side and the doorknob side, and your job is to open the door. Okay, you're going to push on the door to open it. In the first example, it's a straight-on push. The other example, you have to go at an angle. And the third one, you go at a very serious angle to it. And I want to see how the torque changes as I change my angle. Okay, so these ones are pretty easy to throw in there. I have to look at which equation to use. Moment of inertia isn't mentioned. Alpha isn't mentioned. Force and a distance, that is mentioned in the problem. So I'm going to go ahead and pick that one to go with. The last one, of course, deals with vector components, and I wasn't given those. So this is probably my correct option to pick for my equation. So I'm going to go ahead and start with that one. We'll go torque is equal to the magnitude of the force. Now the first one, we're going to push on the door 55 newtons. That's going to be the magnitude of the force. The change in R, this is the radial distance from the axis of rotation to where you're pushing on it. So in this case, we are going to push on the entire door a distance of 0.8 meters. Now for the sine theta, that deals with the angle between the force and the radius. Okay? And you can see here that these make 90 degrees. They're exactly 90 degrees apart. One travels up and one travels over, and they're exactly 90 degrees apart. If we throw that into our calculator, it comes out to be 44. Now, what are the units for torque? Well, we go back and we look, how did we get there? We took force, Newton, and multiplied it by a distance, meter. 44 Newton meters. Okay. Number 2, or part B or whatever, the middle one, I threw up there as well. It's going to be pretty close to the same, but I want you to see how it changes. So in this one, what's the force that we're using? 55 newtons. What's the length of the door? 0.8, right? Axis of rotation, we're pushing on the edge of the door. It's still going to be 0.8. Now the sine of the angle. I think a lot of you would throw in the sine of 20. It's not always the case. You have to really watch and understand what is the problem asking for. I want the angle between these two vectors. Okay, I want the angle between those two. Radius of the door remains horizontal. Okay. The force, though, has now been moved 20 degrees. So the force is coming at about a 20-degree angle. What angle is in between those two vectors? It is not 20. 20 is the difference offset from 90, right? The angle between this arrow and that arrow is the rest of it, 70 degrees. Okay. And it's not always going to be written out like that. Sometimes they're going to give you 70 degrees. Sometimes they give you 20, and they draw it out like that to try and, test your knowledge on it. Okay, but hopefully that makes sense that it's the angle between these two vectors. I have this one going up. I have this one coming in. I'm pushing on that with the other one. Angle between the two is 70 degrees. All right, anyway, let's punch that in. We have 55 times 0.8 times the sine of 70. Do you think it's more or less? It is less. 41.3. We'll go. 41.3 Newton meters. All right, why is it less? Well, you're not putting as much torque. You're not pulling as hard as you can on the door. You're still giving 55 newtons of force, don't get me wrong there, but you're not in the correct position that all 55 newtons is actually taking effect in an effort to turn the door. In fact, the more you continue to increase your angle, the worse it's going to get. It's going to be harder and harder to open the door. Let's take a look at that last one. This is an odd way of trying to open a door, but we'll still do it out. Our force is 55. Our door is 0.8. And our sine of the angle, again, it goes off of the two. Our door, axis of rotation to the end of the door. The length is 0.8. What direction is our force? We're pushing straight back into it. So it's 180 degrees. So what is the torque on this one? We should expect 0 for the Newton meters because this is not how you open a door. Right? Pushing on the door isn't going to do any good when you push on the side of the door. It does not move left or right. You are simply pushing on it. Okay? So hopefully that makes sense a little bit on how sine works and how that 90 degrees is pivotal, to call the pun, on getting torque to exist. Okay, example 3, we're still in torque. In this one here, we have a 0.2 meter round solid disc. So I have, think of maybe like a potter's wheel or something. I'm going to have a disc, and we'll say that's the radius. Well, it said a 0.2 meter. So I'm going to assume that that's the diameter, which means the radius of this will be 0.1 meter. It has a moment of inertia. Now it's a solid disk. So if we go back and we look at our notes, or if I look at the table, a solid disk has a moment of inertia of 1/2 mr squared. So it's given in the problem here, but if it wasn't, we could always look that up or use a cheat sheet or something there for it. I'm pretty favorable to just give you those in there. Anyway, it has that moment of inertia. It starts from rest, and then it reaches an angular speed of 20 rads per second in 30 seconds. What is the torque on this disk if its mass is 5 kilograms? There's the mass, 5 kilograms. It starts from rest, and it's going to start really spinning. All right, it spins really fast in 30 seconds time. And we have to figure out what is the torque on that disk. Well, we come over to our torque equations, and we got a couple of options. We use the R sine theta last time. No force is given in this one. Torque is the angular force. It's the thing we're solving for. There's also no vectors given in this one, but we do have an I. So here's your clue on which equation you want to use. So if we use that first equation, we'll have torque is equal to I alpha. Now I know what I is. I is 1/2 mr squared. It was given in the problem. M would be the mass, 5, and R would be the radius, 0.1. Now, everybody forgets to square the R. I don't know why it's such a common occurrence, but it's 1/2 mr squared. You got to remember the square in there. Guaranteed you'll make the mistake at least once. All right, so this is I. I now need alpha. What is alpha? Oh, it gave me all this info, but I have no idea what alpha is. So I'm going to have to put it as alpha. Alpha is the acceleration. It's something I'm going to have to solve for. It gave me all this other information, though, and I can use kinematics to get to alpha. So if I use kinematics, I'll have theta, omega I, omega f, alpha, and t. Alpha is the thing that I want to find because I can use that in the equation to find torque. What else here? It says it starts from rest, so I know that that initial is going to be a big old 0. I know that it reaches a speed of 20 radians per second in 30 seconds of time. All right, so that means I should be able to find alpha. I've got 3 out of the 4. I got to look back and look at my equations and go, well, which kinematic should I use? And the kinematic is the one that has no displacement in it, which is omega f is equal to omega I plus alpha times t. First equation. And then I just start plugging in. I know that we end with 20. We start with 0. I know alpha is what I'm looking for, and I know that this is 30. All right, which means alpha is equal to 20 over 30, or 2/3, 0.67. And this is radians per second squared. I'll take that alpha, I'll bring it up here, I'll plug it in. Okay, now I just got to plug into my calculator and see what kind of torque our pottery wheel has. Okay, hopefully I plugged that in right. Now I got a small number, which is fine. It's a pottery wheel. We get 0.017. And then torque again, Newton, meter, if we want to do it that way, that's just fine. There would be our torque for our potter's wheel. Okay, so I'm hoping that makes okay sense. Okay, just plugging everything in, using kinematics to find torque. Now I've used the 2 different forms of torque. We can look at doing a cross product next. And that might finish out the torque version or the torque section here of this chapter. Okay. Okay. I realize I put torque is F crossed with R. That's actually the next chapter. We'll get to that in the next portion here. So I won't be doing an example on cross product yet. That'll be for the next chapter. So what I am going to do, though, is look at moment of inertia, being that is in this chapter. Moment of inertia usually can be just looked up. It's usually a common object like a disc or a ball or a sphere or a cylinder or a cone. They all have their own moments of inertia. But every now and then you're going to have to calculate a moment of inertia. And the equation for moment of inertia is the sum of all of the masses times their radius squared, just mr squared. Okay. So if we look at example 4, I've drawn this strange looking cross that's up here. It has two masses, which have this lowercase m that are drawn in blue. Those masses have a radius from the center, a radius b. And then I have these two large orange masses. Those are capital M, and those are a slightly different radius, a radius A. And this whole thing rotates around the y-axis. Okay, so it rotates there. And the question, of course, here would be, what is the moment of inertia, I, for this object? Okay. So we have to calculate out what the moment of inertia is. And then we could use that to find torque. We could use it for a couple of other equations that we have coming up. But we're mainly worried about moment of inertia here. So I know that moment of inertia, I've given multiple masses and multiple radiuses. It's going to be equal then to the sum of the masses times the radius squared. Okay, how many masses do we have? We have 4, which means I'm going to have all of them. I'm going to have all 4. So let's start doing them out. We'll start with the, let's go with the blue one at the top there. We have little m. How far away is little m from the axis of rotation? Well, you might think it's b. Okay, it's there to just prove a point. This is the axis of rotation. So even though it is located b from the center, it is located 0 degrees from the axis of, or 0 meters from the axis of rotation. And it's going to be the same for the small m. That is also on the axis of rotation. So the distance between that object and the axis of rotation is 0. The other two objects, capital M, that one is a distance a from the axis of rotation. And we have a second one, both a distance a. So the total moment of inertia here, this is 0, this is 0. These are two of the same thing. So we get 2 capital M a squared. And that would be our moment of inertia. Now it's just masses times radius squared. So we're going to have kilogram meters squared for our units. And this would be the moment of inertia for this particular object. Now what would happen if I changed it and I said, well, instead of rotating along the y-axis, let's rotate it along the z-axis. Okay, so we'll spin it around like that now. Okay, so instead of spinning on the y-axis, this thing will now spin on the z-axis. How will that affect the moment of inertia? Well, it'll change it a bit. Okay, so it's no longer going to be 2. We're going to have to redo our math and get the new moment of inertia. Now, in that case, we're going to have little m again. And how far away is that axis of rotation? Well, now the axis of rotation is in the center, and little m is a radius b away. And there's 2 of them. So I'm just going to put a 2 in front. Plus, we also have the big M. Actually, we have two of the big M. Two big M's, and those are A away. So you can see by changing the axis of rotation, the point of rotation, the moment of inertia changes greatly. Okay? So there's an example on determining moment of inertia. So we'll pop in example 5 here as well. So in this one, I want to use the parallel axis theorem, the change in moment of inertia. So let's say that you have something that already has a well-known moment of inertia, like a merry-go-round. So that's my best drawing of a merry-go-round. Its moment of inertia is a solid disk, so it's 1/2 mr squared. The mass of the merry-go-round is simply 50 kilograms, and the radius is 2 meters. Okay, that's with it empty. So spinning around the merry-go-round with it empty isn't a whole lot of fun. You want to, of course, get on it and spin it around yourself. And to do that, we're going to change that moment of inertia. So how is the moment of inertia changed if a 40 kilogram person is added at a radius of 1.5? So what I want to do, if the whole radius is 2, I'm going to add a person onto the merry-go-round. That changed its moment of inertia. How much? Well, for that I need to know what the original moment of inertia was, which was 1/2 mr squared, which is going to be 1/2 50 times 2 squared. All right, so the 2 squared is going to give me a 4. Half of that's going to give me a 2. 50 times 2 is going to give me a 100. And then again, that's kilogram meter squared. So that's the initial moment of inertia. By adding an extra person on, I've changed it. How much has I changed it to? Well, I can use parallel axis theorem. And I can say in here, the new moment of inertia is equal to the old center of mass moment of inertia, which was 100, plus anything I add. So the mass, which would be the person I've added, which is going to be a 40. And where did I place that person? Their radius. And that's going to be at 1.5 squared. So the new moment of inertia is going to go up. Okay. Moment of inertia going up means it's going to be harder to rotate. Okay. If we do this out, we have 190 now. Okay. 190 kilogram meters squared. Sorry, my marker's running out. I'm trying to get a new one tomorrow. All right, so 190 kilogram meters squared. We can see how that would affect torque if we wanted to go that route in the problem, because that is dependent on moment of inertia and how fast it accelerates. If you have a motor that's driving this merry-go-round, okay, or a person that's trying to push it around, they're going to apply a certain amount of torque. The larger the moment of inertia means the less acceleration you're going to get. The less moment of inertia would mean more acceleration. Okay, so with lighter people on the merry-go-round, like little kids, you will get a much faster speed. Okay, you will accelerate much quicker than if you have a heavier person on the merry-go-round. Hopefully that makes conceptual sense, and it's a good representation of the parallel axis theorem. You can do this with a rock stuck on a bicycle tire, or gum on your training wheels, or something like that. Okay, it's adding a mass, not in the center, but on the outside of something that is circular and rotating, and then you can see how it affects the things that are around it. And so for the last one here, I wanted to use a rotational kinematic, or rotational energy. My mistake, rotational energy. Up to this point, we've had objects that have done conservation of energy. We've done some friction. Those are all the exact same equations and the same processes that you're going to use for this, except for now you've added one new energy to the list. You have rotational kinetic energy, which is up here equal to 1/2 I omega squared. Okay, so now we have, instead of something flat falling, we have something that's round, like a ball rolling down the hill. And in this case, it's a sphere. We have an I value, a moment of inertia, of 2/3 mr squared. It starts from rest, so it's not rotating and it's not moving. Both W and V are 0, but it's right on the edge. So if I just let the ball go, it will begin rolling down the hill, and it's going to gain speed as it goes. And our question is, how fast is it going at the bottom of the hill? It will go down a total of 3 meters. So we'll have some gravitational there as what's pulling it downward. All right, now, this looks like an energy question. It is an energy question. There's no friction involved, so it's an energy conservation. So I can write EF is equal to EI. And now we have 4 questions to ask ourselves. We have 2 kinetic energies, and we have 2 potential energies. We have to account for all of them. So we are going to have KE, our new one, KER, gravitational, and spring. Okay. Okay. So these are getting really big, but it's all right. We can narrow that down by just asking, is this involved? Do we need to include it? So of course we're going to start with where we always do at the end. The ball is speeding down the hill here and it's at the bottom of the hill. Does it have kinetic energy? Absolutely. It has regular kinetic energy, 1/2 mv squared. And it also has rotational energy. Because it's a ball, it is now rolling, which is 1/2 I omega squared. In the end, does it have any gravity? Can it fall anymore? No, we'll assume that the hill is done and that it cannot fall any further. So we're going to go with a 0. How about springs? I don't see any springs in this problem, so we're going to go ahead and go with 0 on that as well. Okay, final's done. Now we just got to look at the initial. Is it moving in the initial? Nope. There's no velocity. There's no rotational velocity. Both those are going to go to nothing. There is gravitational, though. It is going to roll down a 3-meter hill, so there will be an mgy. And again, no spring at the top. No need to worry about that. Okay. So we've got this now. If I were to start plugging in, I would have to see. Let's see. We have 1/2. I don't have an M. I don't have any mass on my ball. It's not written down anywhere. So I'm going to have to leave it as an M for now. This V final, this is what I want. That is my answer. Okay, so that part's good. What else do we have? We have 1/2 I. I here is 2/3. So 1/2 times 2/3. M again. I still don't have any mass. Times R squared. Okay. I don't have a radius either. Oh, no, I'm not looking good. This is I times W squared. Okay. That's the speed squared. So this is all of I. 1/2, 2/3 mr squared, and then omega squared. And that's equal to, oh, here we've got mass again. G is going to be 9.8. Y is going to be 3. Okay. Well, didn't I get lucky? I've got mass in all of my terms, which means the mass does not matter. I can cancel it out of every single one of my terms. Perfect. Now all that's left is I'm still looking for that V. I still don't have an R. There's a W floating around in there. And now I've got a number there. So I've got to handle something in here, right? I need a number in here in order for this to work. So what can I do to change this? Okay, well, I know that omega can be flipped back and forth. I can go from angular to linear, right? How do we go from angular to linear? We throw an R into the equation. So I know that V is equal to R omega. It's on the formula sheet. It's from linear to angular. Well, this is omega squared. So let's see. If I solved for omega, I'd have V over R. which means omega squared would be v squared over r squared. Okay, let me make that substitution. That'll get me into v. I'm going to have 1/2 vf squared plus 1/2 of 2/3. M is gone, so I'm going to have r squared. And then I'm going to take this w and I'm going to change it out for this w, which is going to be v squared over r squared equals 9.8 times 3. Okay, that got me a little better because now my r squared and r squared can cancel, and I'm just left with v finals. All right, now we're getting somewhere. Now the only thing left here is our v finals. So let me go and erase this so I have some more room. Hopefully you got notes, you know how we're doing this. And let's start plugging some stuff. We'll just keep going on the math. That's all we can do. So I've got 1/2 v final squared plus what's 1/2 of 2/3? Okay. 1/2 of 2/3 is 1/3. You have 2/3, you take 1/2 of it, 1/3. And then this is going to be vf squared. Now the r squareds have canceled. And this is equal to 9.8 times 3. All right, so I've got 1/2 plus 1/3. What does that give me? All right, if I take 1/2 and I add 1/3 to it, I have to find a like denominator, which is going to be 6. So I'll have 3/6 plus 2/6. I will have 5/6 vf squared. And now 9.8 times 3 gives me 29.4. Okay, now I just need to multiply by 6, divide by 5. And that will give me v squared equaling 35.28. And now there's only one thing left to do, and that is to take a square root. And that will give me a final velocity of what I'm looking for, which is 5.94. And since it's a normal velocity, it will be in meters per second. And that is my final velocity for the ball at the bottom of the hill. So it's a bit more work. It's a bit more involved. There's a couple of tricks in there to get rid of masses. There's a couple of tricks in there to get rid of the radiuses. I really don't need to give you a whole lot of information in these problems anymore and have you do a whole lot of math based on just observation and knowing where to go. Okay? All right, so hopefully you learned a bit on that one. You'll have a few more in the homeworks. We can also make this much more complicated if we wish. We could have added a spring up here that was originally pushing the ball with some initial velocity, and maybe the ball was already rotating. Maybe there's friction involved. Maybe there's a spring down here. All right, who knows? We can change it up and make it much more difficult, but I'd rather keep things simple for you. All right. Knowing how we could change the problem, though, is key. Right? How we can adapt to different problems, because you're not going to get exact problems like this on tests or homework. You're going to have to be able to adapt. All right, hopefully that was good for Chapter 6. I know it's a lot of new stuff, but it's a lot of old stuff as well. All right, I think I'll end there for you.